Well, students, let us see some exercise problems from chapter 3 in this tutorial session. Let us take up the problem number 21. Problem has 3 subdivisions. Out of these, we have already finished the subdivision 1 and 2 in one of our previous tutorial sessions. Let us take the subdivision 3. The problem says that you have a n cross n matrix A with real entries, and you are also given that the condition number of the matrix A with respect to the Euclidean norm is given by 1. Then we have to show that all eigenvalues of A transpose A are equal. We have to also deduce that the matrix A is a scalar multiple of an orthogonal matrix. It is given that kappa 2 of A, that is the condition number of A with respect to the 2 norm, L2 norm, that is the Euclidean norm, right, is 1, and that implies that norm A, it's a matrix norm subordinate to the L2 norm, into norm A inverse is equal to 1, right? And that implies norm A 2 is nothing but 1 by norm A inverse. Recall that the subordinate norm to the L2 norm is defined as the maximum of all the eigenvalues lambda I of the matrix A transpose A, right? So that is how we have stated as a theorem. So we will directly use that theorem here to get the formula for the 2 norm, and that implies that norm A inverse is defined as maximum of root mod mu I. What are mu i's? Mu i's are the eigenvalues of the matrix A inverse transpose A inverse, which is equal to A transpose inverse into A inverse, that is equal to A transpose inverse, right? So mu i's are the eigenvalues of the matrix A transpose inverse. That implies 1 by mu i's are the eigenvalues of the matrix A transpose. Since the eigenvalues are same for a matrix and its transpose, therefore mu i's are also the eigenvalues of A transpose A. We have already assumed that lambda i's are the eigenvalues of A transpose A. Therefore, 1 by mu i's are actually equal to lambda i's, right? Therefore, maximum of root mod mu i's are nothing but maximum of root mod 1 by lambda i's, right? And that is achieved at 1 by minimum of root mod lambda I. Therefore, we can say that norm A inverse is equal to 1 by minimum of root mod lambda I. And that implies that 1 by norm A inverse is minimum of root mod lambda I. Now substitute this into this equation. We get norm A, which is maximum of root mod lambda I is equal to 1 by norm A inverse, which is minimum of root mod lambda I. So the maximum and minimum are taken over all I is equal to 1 to n, right? This implies that mod lambda I are equal, right? That means mod lambda 1 is equal to mod lambda 2 is equal to, and so on, mod lambda n. Remember that lambda i's are the eigenvalues of the matrix A transpose A, which is a positive semi-definite matrix. Also note that we always assume A to be invertible, right? That implies that all lambda i's are positive. That implies lambda 1 is equal to lambda 2 equal to so on till lambda n, right? So this is what we have to show that all the eigenvalues of A transpose A are equal, right? So this is what is asked for us to prove, and we have proved it. Now the other part is rather very easy. Further, deduce that A is a scalar multiple of an orthogonal matrix. How will you do that? So to prove that A is a scalar multiple of orthogonal matrix, it means up to a scalar multiple, you have A transpose A equal to A transpose equal to I. That is what we wanted to prove. But what we have shown, A transpose A has all its eigenvalues equal, right? Therefore, A transpose A will be similar to a diagonal matrix whose all the diagonal elements are equal. Let us call these eigenvalues which are equal as lambda. Then you can see that A transpose A can be written as P and then the diagonal matrix lambda, lambda, and so on, lambda, 0, 0, and P inverse, right? We can find a invertible matrix P such that the matrix A transpose A can be written like this. You know this. You can see that A transpose A is also a symmetric matrix. Now you remove lambda outside this and we can write it as Pi P inverse, that is nothing but lambda I. Therefore, A transpose A is lambda times I, and that implies you bring lambda to the left hand side and write it as 1 by root lambda A transpose into 1 by root lambda into A. That will be equal to I, right? Now you observe 1 by root lambda into this and call this as A transpose lambda. Let me call this as, and this as A lambda, and this is A lambda transpose. Therefore, A lambda is equal to I, right? And similarly, you can see that A lambda transpose A lambda into A lambda transpose is also equal to I. The same idea you can use, and also use the fact that a matrix and its transpose both have the same eigenvalues. You can prove that A lambda transpose is also equal to I. And therefore, A lambda is an orthogonal matrix. Okay, so that implies that A lambda, which is nothing but a scalar multiple of A, is an orthogonal matrix. So that completes the proof of this result, third subdivision of the problem number 21 in chapter 3. Next, let us take the 32nd problem. We have to find a n cross n matrix B and an n-dimensional vector C such that the Gauss-Seidel method can be written as xk plus 1 equal to b into xk plus c. If you recall, each component of the Gauss-Seidel iterative method is given by xj k plus 1 is equal to 1 by ajj, that is, we are dividing both sides by the diagonal element of the matrix A, into bj, that is the jth component of the right hand side vector B, minus, now we are bringing all the non-diagonal terms to the right hand side, and then we are splitting them into two parts. One is the part where the components are already calculated in the present iteration, that will run from, say, L is equal to 1 to j minus 1, right? When you are calculating jth coordinate of the vector x, you have already calculated the coordinates of x which are less than j. Therefore, we take that as the values computed at the present iteration itself. So k plus 1 will come, and the term which involves all the coordinates that are yet to be computed in this present iteration, that goes from L equal to j plus 1 till n, right? So that will be taken with the corresponding coordinates of the previous iteration. So you have xl k, and this should happen for all j equal to 1, 2 up to n. Remember, ajj should not be equal to 0. These are all something which we always assume when we are building the methods of this form. And also we have k is equal to 0, 1, 2, and it will keep on going like this. Now, when you observe the general form of the iterative method, you can see that all the terms which are involving the previous iteration, that is kth iteration, should be kept on the right hand side, and all the terms that involves the k plus 1th iteration, that should be kept on the left hand side, right? So that's the key idea. So what we do is we will bring these terms to the left hand side and write xj of k plus 1 plus sigma L equal to 1 to j minus 1 ajl divided by ajj xl of k plus 1, right? And what remains on the right hand side is bj by ajj, that is coming from the right hand side vector, and it also involves another term that is given by minus sigma L is equal to j plus 1 to n ajl divided by ajj xl k. So now this is going to contribute to bxk, and this is going to contribute to our vector c. And somehow this we have to write in the matrix form, something like L into x, and then we should see that L is invertible. So you multiply both sides by L inverse. Okay. In other words, what I'm trying to say is we can write this as more precisely in the matrix form, L times x vector k plus 1, right? This is one typical term. This goes for j equal to 1, 2, and so on, right? So I'm just putting it in the matrix form, is equal to this part, which is my b tilde say, plus I'll combine all these terms and make it as u into xk. Why I'm giving this notations L and u, you will come to know that. you can carefully observe and write how this L will look like. I leave it to you to do that. L is going to be of this form: 1, 0, 0, and so on, 0, A21 divided by A22, then 1, that is the second equation, right? And then everything else is going to be 0 because they all are going to sit on the right hand side, right? Therefore, they all will contribute to 0. And you have A31 by A33, A32 by A33. Why they all are coming to the left hand side? Because when you are computing the third component, you have already computed the first component and the second component, right? Therefore, they all are taken from the present iteration itself, that is k plus 1 itself. That is why they are contributing to the k plus 1 part, and therefore they were pushed to the left hand side. That is how these two terms are surviving in this. And then the diagonal term, which is 1, and then the rest all will become 0 because they are kept on the right hand side. They contribute to the coordinates from 4 onwards. So they are not yet computed in the present iteration when we are computing the third coordinate. Therefore, we have substituted the previous iterations values. That is why they were kept on the right hand side. So you should just understand how this matrix is formed. So similarly, you can go on, and when you are at the last coordinate, that is the nth coordinate, you can see that everybody else are computed already. Therefore, you are substituting the present iterations value in all the components from the component 1 to n minus 1. Therefore, all will come and sit on the left hand side and so on. And the diagonal element is anyway 1, right? So this is precisely the left hand side matrix L. Now you can understand why I gave this notation L for it. It is a lower triangular matrix. And also you can see that it is invertible. That's more important because we want to put finally our matrix equation in this form where the left hand side is just an identity matrix, right? So I can multiply both sides by L inverse and thereby make the left hand side coefficient matrix as the identity matrix. For that, I am very happy that L is invertible. And what is U? U is going to be minus because there is a minus term here, and I have taken plus here. Therefore, I will keep that minus in the definition of U itself. Now, once you understood how to construct L, it is very easy to now construct U also. While computing the first component, you have kept all the components on the right hand side because you have not computed any component. Therefore, you will take all the information from the previous iteration. Therefore, you have all the terms sitting on the right hand side. So you will have 0, A12 by A11, A13 by A11, and so on up to A1n divided by A11. Right? And similarly for the second one, well, the first term was computed using k plus 1th iteration. Therefore, it already went to the left hand side and made a 0 here. And the diagonal is always kept on the left hand side. Therefore, that is also 0. And what happens to the rest of the things? Well, they are surviving on the right hand side. So they will sit here, A23 by A22 and so on till A2n divided by A22. And it goes on like this. And at the last equation, nobody survives on the right hand side because everybody, including the diagonal element, which is always there on the left hand side, have gone to left hand side. Therefore, that part will be 0. And what is B tilde? B tilde is nothing but the column vector having B1 by A11, B2 by A22, and so on, Bn by Ann. See, all this goes with the assumption that the diagonal elements are non-zero. Okay, now you write that L is invertible. Therefore, you can write xk plus 1 is equal to what I'm doing. I'm just multiplying both sides by L inverse. Therefore, we can write the above equation as x k plus 1 is equal to L inverse B tilde plus L inverse U xk, right? Now I will take this as my vector C, and I will take this as my matrix B, and then I can write xk plus 1 is equal to C plus B into xk. So that is what we are supposed to show in this problem, that write your Gauss-Seidel method in this form, which we have written here. Next, let us take up the problem number 37. We have to use Gerschgorin circle theorem to determine the intervals in which the eigenvalues of this matrix belongs to, given that A has all real eigenvalues. And then further, the question asks us to show that the power method can be applied for this matrix to find the dominant eigenvalue without computing the eigenvalues explicitly. That is, without computing eigenvalues explicitly and seeing whether all the hypotheses of the theorem are satisfied, you somehow check the hypothesis that the power method sequence do converge to the dominant eigenvalue, provided if you choose the correct x naught, right? So you anyway have to choose a correct x naught, but the other two hypotheses can be checked somehow without explicitly knowing the eigenvalues. That is what is the question. And once we do that, compute the first three iterations of power method sequences. Here, it has not given what initial guess that we have to keep. That is, what is x naught is not given in this problem, but we will take some x naught as per our choice. But let us start with the first part. That is, we have to use the Gerschgorin circle theorem to find the intervals in which the eigenvalues lie. Let us first construct the Gerschgorin disk. D1, the first disk, is given by the set of all z in the complex plane such that z minus the center is going to be the diagonal elements. Therefore, the first disk center is A11, which is given by 0.5 in our matrix, and that is less than or equal to, the radius is the sum of the absolute values of the non-diagonal elements of that row, right? So therefore, in this case, it is going to be 0.2. That is the first disk coming from the row 1. The second disk, D2, is similarly obtained as the set of all z in C such that mod z minus 3.15 is less than or equal to 1, right? D3 is equal to the set of all z in C such that mod z minus 7.43. Okay, therefore it is plus 7.43. Don't put minus 7.43. For center, we should not take modulus. Only for radius, we have to take the modulus. And this is going to have the radius as 0.57. And these are the Gerschgorin disks. Let us draw the Gerschgorin disk and see how they look like. The first disk center is at 0.5. The second disk is going to have the center at 3.15. The third disk center is at minus 7.43, right? Now we can see that the disk 1 has radius 0.2. Let us say it looks like this. Assume that it's a circle. The second disk is going to be centered at 3.15 and the radius is say 1. So it looks something like this. And the third disk is going to look something bigger than the first one but smaller than the second one, right? So roughly they look like this. Since all the circles are disjoint, you can see that eigenvalues are going to be distinct, because as per the Gerschgorin theorem, one will lie somewhere in this disk, that is lambda 3, say. We will call this as D3, and one will be sitting somewhere in this disk. Since we have already given guarantee that they are real lines, I am putting them on the line. They can be anywhere on this line lying in the disk. Okay, I'm just randomly drawing it like this, lambda 1, right? Now, lambda 1 is therefore belonging to the disk D1, lambda 2 is in disk D2, and lambda 3 is in disk D3, and therefore you can see that they are distinct. Since all the eigenvalues are real, we can see that lambda 1 actually belongs to the interval 0.3 to 0.7, and lambda 2 belongs to 2.15 to 4.15, right? And lambda 3 is going to be in -8 to -6.86. So this is what we infer from the Gerschgorin circle theorem. Now, the first one implies first eigenvalue is going to be bounded by 0.3 to 0.7. Actually, I need not put modulus here. And similarly for lambda 2, the lower bound is going to be 2.15 and the upper bound is going to be 4.15, right? And similarly, the third one is going to have 6.86 as the lower bound. Here modulus is required 8, right? So these are the bounds for the eigenvalues of the matrix A as far as Gerschgorin theorem applied to A is concerned. Similarly, you can also get the bounds using the Gerschgorin circle theorem applied to A transpose. That may be having a better bound, or combining these two, you can surely have a better bound than this, or at least as good as this, right? Now, since the intervals are disjoint, mod lambda 3, remember, lambda 3 is sitting on the negative side. Sometimes what happens is when you take modulus, they may go and intersect one of these. Okay. Say for instance, instead of 7.43, if it was centered at -3 somewhere, then when you take the modulus of lambda 3, that may be sitting with the bound of D2, right? So therefore, you have to be careful in seeing whether after taking modulus, they are distinct. Okay, so that's one key point that you have to keep in mind. Here, it is very nice because even after taking modulus, you see that lambda 3 cannot have an intersection with any of these intervals of lambda 1 and lambda 2. That is how we concluded that lambda 3 will be strictly greater than lambda 1 and lambda 2. Okay, that part also you have to take care. So all the eigenvalues are distinct. Therefore, the corresponding eigenvectors will span R3. And since they are coming with this kind of order, you can see that the dominant eigenvalue, which is lambda 3, is distinct and unique, more importantly. Therefore, power method can be used to obtain the dominant eigenvalue lambda 3 and a corresponding eigenvector. Now, of course, it depends on what x naught that you take, because if the x naught that you choose is in such a way that C1 is equal to 0, then you cannot do. But as such, from this information, we can see that power method can be used, provided you choose a correct x naught. That's a different question altogether, but power method can be used. That's what is concluded from here. So what we were asked, using Gerschgorin circle theorem to determine the intervals of the eigenvalue, that we have already determined, show that the power method can be applied for this matrix to find dominant eigenvalue. Okay, that also we have seen that power method can be used. Now, compute two iterations. Well, it was not given what x naught that we have to choose. Ideally, it should have been given, but I have chosen x naught to be 1, 1, 1, and I have made 3 iterations. You just check whether the computed values are correct. Y1, which is nothing but a of x naught, and remember I have taken x naught as 1, 1, 1, and that leads to y1 as 0.7, 2.15, and minus 6.86. From here, I get mu1 as, remember, you have to take the maximum norm of y1. So let me write maximum norm of y1 is actually equal to 6.86, and therefore mu1 has to be minus 6.86. Why? Because you have to take the value of that component at which the maximum norm is achieved, not just maximum norm. So it is minus 6.86. Once you have this, then x1 is going to be equal to y1 divided by mu1, right? So that is going to be minus 0.10204 minus 0.31341, and the last one is 1. So that is the first iteration. For the second iteration, we have to find y2 first, that is given by a into x1, and that is numerically going to be 0.14898 minus 1.98724 and minus 7.48816. And that leads to mu2 as, again, from this component, and that is going to be minus 7.48816, and therefore x2 is going to be y2 by mu2, and that is minus 0.0199, 0.26538, 1, and the iteration 3 is given by y3 is equal to, again, ax2, and that is 0.19005 minus 0.16405 and minus 7.44134, and that again leads to mu3 as minus 7.44134, and therefore x3 is equal to minus 0.02554, 0.02205, and 1. Okay, so that is the output of the first 3 iterations for the power method using the matrix A given in this problem.